Hello, linear algebra student. This video is for chapter 5.2, part 2. We finished in the first video about finding characteristic equation, characteristic polynomial, which is the determinant of a minus lambda I, and then figure out how to find all the eigenvalues from the polynomial. And then after you find your eigenvalue, then you can go ahead and solve for the eigenvectors, and you will have everything. One thing that we want to get ready for 5.3 is a concept of similarity, which is the last concept. You see how if I have a matrix, which is a part of the transformation of Rn, and then I can have eigenvalues for one. If I have another matrix, I can have other eigenvalue. So we can relate two matrices together if we can find a invertible matrix P such that A is equal to A is equal to P times B, P to the power -1. So this is what we're looking at. If I can find a P such that when I multiply P in front of B and then multiply P inverse, and I get exactly equal to A, then I say, or we can say B is equal to P inverse A times P. Then we can say A and B are similar. So if A and B are related in such a way that A is equal to P times B and then P inverse, then A, B are similar. And it can be proved, I'm going to prove it here, that if A and B are similar such that this exists, P exists, and you can find it, then they would have the same eigenvalues actually. So let's look at this, how to prove it. So if B is equal to, because A equal to PB, P inverse, so B would equal to P inverse AP. Why? Let's start from here. A equal to P times B times P inverse. So you can find something like this. You will multiply P on this side, multiply P on this side, then I have AP equal to PB. And then you multiply P inverse on the left hand side, then you have a P inverse. So B would become P inverse A and times P, right? So they're actually the same thing. Then if I wanted to find the determinant of B, I would say determinant of B minus lambda I. But B minus lambda I is actually P inverse AP. And then I can also do P inverse and times P on both sides of I. What happened is lambda I is just a whole bunch of, this is kind of like a, lambda is just like a scalar. So P inverse times I times P is exactly equal to I, right? So that's equal to lambda I. So this is the meaning. And then you can see that you can factor P inverse and P out and factor A minus lambda I in the middle. And due to the properties of determinant of A times B is equal to determinant of A times determinant of B times determinant of C here. So we can split them into individual part. Determinant of P times P, determinant of P inverse actually cancel each other. So because this is 1 over determinant of P, so we would have determinant of A minus lambda I, which is the same characteristic equation. If they have the same characteristic equation, A and B has the same characteristic equation, then the two matrices will have same eigenvalues. But notice that the opposite is not similar. If two matrices have similar eigenvalue, they may not be similar. So let's do an example. So I have a vector B, I have a matrix B and a matrix A. And for some reason, I can find P. So let's verify if this would work. But let's verify, show that A and B are similar, and this is the B that is given. To check this out, if P times B times P inverse is equal to what? So I would use 1, 0, negative 2, 0, 1, 1, 0, 2, 3 times B, which is 1, 0, 0, 0, 2, 0, 0, 0, negative 5. Then P inverse is 1, 0, negative 2, 0, 1, 1, 0, 2, 3. Inverse. So you can use the decimal matrix calculator to multiply them. This is where I have B here. I call the P A 1, 0, negative 2, 0, negative 2, 0, 1, 1, 0, 2, 3. And I have A inverse, so I multiply A, B, A inverse. It becomes 1, negative 24, 12, 0, 16, negative 7, 0, 42, negative 19. So that is exactly equal to A. So A, B are similar. So if A, B are similar, then let's check the eigenvalue. So the eigenvalue of B is obviously very easy because it's a triangular matrix. So it's just off the diagonal 1, 2, negative 5. What about the eigenvalues of A? That is a little harder, right? So we will say eigenvalue of A would be solving determinant of A minus I lambda equal to 0. So that means 1 minus lambda, negative 24, 12, 0, 16, negative 7, 16 minus lambda, and then 0, 42, negative 19 minus lambda. So find this determinant, set it to 0, then I can solve it. So this would equal to, expanding the first column, equal to 1 minus lambda times the determinant of, so I cross out this row in this column, 16 minus lambda, negative 7, 42, negative 19 minus lambda. So that is equal to 1 minus lambda times 16 minus lambda, negative 19 minus lambda, plus 42 times 7. So simplify it, equal to 1 minus lambda. 16 times 19 is 10 times 19 is 304. So negative 304 minus 16 lambda plus 19 lambda, so plus 3 lambda. Minus lambda is plus lambda square plus 42 times 7 is 297, 294. So after you simplify, it will be 1 minus lambda. This will be negative 10, right? Now lambda square plus 3 lambda minus 10. So you simplify it. Oh, not enough space. This would equal to 1 minus lambda, plus 5. Oops. Lambda minus 2. So the eigenvalues are 1, 2, negative 5, which is the same as B. So solve. Okay, they are similar. They are similar, and also they have the same, and that implies that they have the same eigenvalue. So anytime if you multiply an invertible matrix in front and the back to create another matrix, that new matrix will have the same eigenvalue as your original one, meaning the eigenvalue of B is the same as eigenvalue of A.